All right. So so the last thing we saw was I sort of left it at this question, right? So I said consider the length clauses that we have defined earlier. This we have already seen this, right? So, but the last time we saw it, we gave an actual concrete list here, and we asked for the length. The question that I'm asking now should be one slide before. So the question that I'm asking now is, what is the first result of the query len a comma 2, where a is a variable? Here is the answer. Anyway, so what is the answer for this one? Did someone manage to work it out yesterday? Yeah, Sarthak has the right answer. So the answer is the important thing is the first result of this query is going to be 2, right? So let's see why that is the case. I think it's important to understand why this one is the case. So let's go ahead and do as we did earlier. So we'll trace len a comma 2 by hand. So we start with len a comma 2, right? So this is the query that we want to satisfy. If you sort of look at the two options, the first one we have is going to be len empty is 0, right? A, the variable a unifies with anything. It also unifies with empty list. That's fine. But 2 doesn't unify with 0, right? So 0 does not unify with 2 because both are considered to be atoms, and atoms don't unify. Atoms don't unify if they are not the same. So this is going to come back. So I'm going to draw an X here just to indicate that that doesn't work out. What about the second clause? So we have an option, right? So the thing that we should remember is there was always two options here. So I'm going to mark it with a star here to indicate that there is a choice point over there. And let's do the second clause now. So the search is going to continue, and then it's going to try into T1, N1, then of T1, M1, N1 is M1 plus 1. Okay, so we are first going to try to unify. This term here at the head of this rule, right? And because a is a variable and we have a term here, this one happily unifies. So we don't need to particularly consider that. What we do know is that N1 is going to be unified with 2. So let's transfer that over to the other side. N1 is going to be 2. But beyond that, we don't know anything about anything else. All of these are variables which haven't been unified yet. So what the search is going to do is going to try the first of the goals. So we have two goals here. So we're going to try the first goal, which is going to be len of empty is 0. The observation here is both of these are variables, right? So this one unifies happily with T1 and this one unifies with M1. So let's get back and say T1 is going to be empty and M1 is going to be 0. So if you use this unification information for the second goal, the only thing that we have is M1 is 0, right? And if you focus on this term, right, it says 2 is 0 plus 1. So because we have the is operator, we are going to numerically evaluate 0 plus 1, which is 1, and we are going to unify 1 with 2, and that doesn't work out, right? So 1 does not unify with 2, so this is going to fail. But again, the observation is that we have another choice here. So we are going to undo the unifications that we've done so far. So all this gray bit will go away, right? and we are going to try the second clause now, which is going to be len of T2 N2 len of T2 M2 N2 is M2 plus 1. Okay, so now all we know, so what we're going to try to do is try to unify this goal, right, where everything is a variable, right? So T1 and M1 are just variables. We are going to unify with this. This one happily unifies, right? So we are going to get this whole thing is T1, right? And this, just to explicitly write it out, this whole thing is A. M1 is here, so N2 is going to be M1, right? What do we have here? So we have this one as M1. T2, let's leave it as T2 for now. And now unification has succeeded on the head, right? So Prolog is going to continue with the body. So the first goal again is going to be no particular special information. So let me do it here. So this is len of empty is 0, right? And empty unifies with T2, 0 unifies with M2. You get the result back. So what do we have? We have this is empty list, right? M2 is going to be 0. We transfer it over there. M2 is going to be 0. So now we have an is operator. So M1 is going to be let me write it out. M1 is going to be 1, right? Because 0 plus 1 is 1. This is a variable, so this unifies with 1. If you take the result of all of those and apply it to the head of the rule, M1 is going to be 1. So what is T1, right? So if you look at this, T2 is an empty list. And T1, we don't care about what T1 is. We know that unifies with some element. So all we know about T1 is that T1 is unified with a singleton list. So if you read what we have here, right, what we found out is, if you give me any singleton list, that length is going to be equal to 1, right? That is what this particular thing is saying. So bring it down. We know M1 is 1. T1 is going to be the singleton list, right? And if you use the information here, M1 is 1. So 1 plus 1 is 2. That unifies happily, right? So this 1 plus 1 is 2, and 2 can be unified with 2. So that goal is done. So use the result of the unifications in the head of the rule. So we know T1 is a singleton list, and A is some element const to the singleton list T1, right? Some element const to the singleton list T1. So A is going to be some element. Actually, I'll write it this way: some element and some other element. Right? It is a list which has precisely 2 elements, and we don't care about what those elements are. And this comes down, and what we have as a result is element with a list with 2 elements, and we don't particularly care about those elements. And that is what we have. So that's the reason why the result of the first result of this query is going to be A equals any list, any list which has 2 elements, and we don't care about what those elements are. Okay. So naturally, this first is should hint you to something about the second. If I say something is first, there must be a second. So let me ask the question, right? What is the second result of the query? Len A, 2. Yeah, Harini has the right answer. So query runs forever, right? So this is quite interesting, right? So this is So non-termination is a is an indication of Turing completeness, right? So you have something that runs forever, which means the language is Turing complete. So we know that because of this, we will see that Prolog is Turing complete. Actually, we'll see that it runs forever, right? So here is what will happen. So I stopped here, right? The observation again is that there is a choice point here, right? And we haven't explored that choice point. So Prolog, what it will do is it will start undoing all the results, right? Let's all erase all the gray bits. Erase this, all these unifications. And then implicitly what Prolog is going to do is it is going to consider that this particular result is going to um, it considers as if that particular result was not satisfied using that goal. So that is how Prolog convinces itself to explore further. And let's explore further, right? What is the second clause that we have for this goal, which has a choice point? The second clause will have the same shape, right? So let me write it out. Then of T3 M3, M3 is M3 plus 1. Yeah, and the observation is that this one happily unifies. So this unifies with T2, this unifies with M2. And if you transfer, you don't need to transfer anything now. We'll just see how it works out. So, oops. So, yeah, okay. So now we go to the first goal in the body, which is T3 M3. So let's do len of MT is 0, that unifies, so that comes back. Right? And of course, we have a choice point here. Let's also mark that out. T3 is empty list, M3 is 0, right? M3 is 0, so N3 is 1. If N3 is 1, this is 1. And because T3 is a empty list, T2 is going to be a singleton list, right? And if you bring that down, what do we have? T2 is a singleton list. M2 is 1. So if you use the results on the second goal, M2 is 1. So 1 plus 1, 2. So M1 is 2. So M1 is 2. And T2 is singleton list. T2 is a singleton list. So T1 is going to be singleton list appended to some element. So this is going to be a list with 2 elements. Right? And if you bring that down, so T1 is going to be this. M1 is going to be 2. If you use this on the other side, M1 is going to be 2. Now is where things get stuck, right? So if you look at this goal, it says 2 plus 1 is 3, and we are going to unify 2 with 3, and that doesn't unify, right? So we have to undo everything. So Prolog says, okay, I can't continue further, but I know that there was a choice point all the way up here, right? And let's do this for the completeness sake. So we erase everything that we have here. Erase this, erase this, erase these, erase this, erase this, erase this, right? And consider this to have failed, so that we can explore further. And if you continue further, this will be len of T4 N4 is len of T4 M4 N4 is M4 plus 1, right? The observation to make here is that the thing that you see here, right, is almost the same as the one here. Of course, we need to erase these as well. So what you're going to do is essentially you're going to count the number of levels, right? You had 3 here, and the unification failed at this point, right? Where we tried to unify 2 with 3. Now, because of this additional clause here and this +1 here, we are going to end up with 4 here, which will be 2 is 4 plus, 2 is 3 plus 1. 2 is not, 2 doesn't unify with 4, right? So we are going to undo everything. But again, the observation is that there is a choice point here, and Prolog is going to keep on continuing, yeah, and loop forever. So this is how we get the looping forever. So the first result is fine. That is what we expected. But because there were other choice points, Prolog is going to continue looping and looping, and it's never going to terminate. Prolog cannot, in particular, Prolog cannot know that this search will not terminate, because SLT resolution does not do any sort of notion about termination, right? It has a certain set of rules. It's going to keep on continuing, and if it continues, it enters into this infinite loop. And that's why the very second result of this query runs forever. Okay. Any questions on this one so far? Okay. If there are no questions, let me continue. Yeah, this is what I did. And of course, you can limit the number of results, right? Because we know that for certain queries, we know there can be infinite loops, but we can still get useful results out by limiting the number of results. So I say here, get me the result of this query where I limit the number of results to 1. And this tells me that A is 2 variables, right? And because variables unify with anything, it just says that it happens to be A is a list. A has exactly 2 elements, and I don't particularly care about what those elements are. And those are just left as variables. Okay, so that is all I wanted to say about lists. So we'll see more lists as we go along, because list is sort of has enough complexity to convey all that I wanted to say about Prolog. So we'll see more about lists in the next lecture, but that is all I wanted to say about lists in this lecture. Any questions? Cool. Okay, so let me continue. Okay, so I don't think. Okay, so this should work. Okay. Yeah. Okay. So we have seen a lot about how control works in Prolog, right? As we said, Prolog is basically your logic that you express, the logical program, and the Prolog interpreter having to choose to pick the goals to resolve, and then the rules to resolve, right? There are 2 options, and this is what we mean by control. And we will look at some properties of this control in this lecture. We will also try to look at an abstract interpreter for Prolog. So we saw SLT resolution that was from a logical standpoint. We are now going to look at the Prolog interpreter from a practical standpoint. How would we go ahead and implement something like Prolog? Right? Prolog is, if you think about it, it's a very simple language. At its core, right? The core of Prolog is simple. Of course, there are lots of bells and whistles. So what we will do in the last assignment, so the next assignment will be an assignment on some list programming, right, in Prolog. And the last assignment will be implementing a Prolog interpreter in OCaml, right? So in this lecture, towards the end, what we will see is how do you actually build an interpreter for Prolog? Like, what are the pieces? And we call this abstract interpreter for Prolog. And we will see what those what that interpreter is and why we call it abstract. Okay, so before any of that. So what did we see in the last class? We saw programming with lists. We also saw the properties about arithmetic. We had this idea of backtracking and choice points, using which Prolog produces more than one result. Okay, so in this lecture, we are going to look at control. So we are going to look at the some interesting behaviors that happen to appear when you reorder the rules and goals in a Prolog program. So although there is a very logical reading of the declarative statements that you write down as a Prolog program, because of the interpreter having to choose one of the goals and rules in some order, we will see interesting behaviors. So I will give you some examples that sort of highlight those behaviors and sort of explain what's going on, right? To give you an intuition. So one thing you will encounter when doing the next assignment is that the order in which you present the rules and goals really matters, and this sort of covers some basics so that you can wrap your head around what is going wrong when you write these programs. So, and then finally we'll actually describe an abstract interpreter where we describe unification and substitution. And you will use this information, this abstract interpreter, and you will encode this interpreter in OCaml, and you will have your own Prolog implementation at the end of it. Okay, so as I mentioned previously, right? So in a Prolog program, you have logic, which is how we express the program, and you have control, which is what Prolog chooses the rules and goals. As I mentioned in, I think, the first or the second lecture, there are several options in order to pick the rules and goals. SLD resolution does it in one way, but you could have done it in n number of various ways. And different Prolog implementations vary based on the choice of rules and goals. Okay, so we are going to study just SWA Prolog's implementation, right? We are going to study something very specific to this, but you can sort of extrapolate this information to other Prolog implementations and understand how they work. So rule order, there are two properties, rule order and goal order. Rule order just says that given a program with a collection of facts and rules, it is the order in which you pick the rules to unify, right? And in SWA Prolog, we always go from the order in which the rules are written down. So you go from first to last, right? In the order in which they appear in the program. And goal order is whenever you have a set of goals to resolve. So we had several examples previously, right? When you unify with the head, the body might have more than one goal. And we always said we will pick the first leftmost sub goal in order to explore. And the idea is that, so this is one of the choices, right? You could have picked any goal to proceed, but SWA Prolog always picks the leftmost sub goal to proceed. And the observation is that rule order and goal order influences the program behavior. So we will see how this works out, of course, with examples. So here is a definition of substring in Prolog, right? So you have this string, it should be a subsequence, not a substring. Anyway, so consider that you have a list Z, right? And X happens to be the prefix of Z, and S happens to be the suffix of Z, but it is also a subsequence of Z, right? It is some subsequence of this list Z. We can specify this S declaratively in two seemingly equivalent ways. So we can say that S, so there is a prefix of Z called X, right? There is a prefix of Z called X, and S happens to be the suffix of X. S is the suffix of X, right? And you can also describe it as, so what we want to describe is the subsequence, right? Subsequence S of Z. We can say there exists an X. I don't care what that X is. There exists an X such that the S that you're interested in is the suffix of X, and that X happens to be a prefix of Z, right? So the only difference between these two formulations is the order in which I've written down these statements, right? So prefix and suffix appear here. I've just swap those orders here. If you think about just the pure logical encoding of these statements, these are equivalent, right? If you just think about first order logic, of course these are equivalent. But if we encode this in a Prolog program, you'll observe interesting differences. So here is how we do it. Again, I am writing substring here, but this should actually be a subsequence. But I hope you get the point. So first we define the append. Append is what we saw in the last class, right? It's the same definition. And similarly, we've seen the definitions of prefix and suffix also in the last lecture. So I'm going to load all of that up. Oops, why is this? So kernel has appeared to have died. Okay, and it restarted magically. Okay, that's good. So I've added 4 clauses. And now what I want to describe is that I'm defining essentially this on a concrete list. So I'm defining this on a concrete list. So the observation is that this logical reading works mostly, right? On most of the examples, they usually produce the same result. So I'm saying that ABC is a prefix of ABCD, right? And S happens to be a suffix of ABC. So I'm asking Prolog, give me all suffixes S such that this particular query is satisfied. Okay. So if you run this, actually this is sort of true, right? We don't have any variables here, but just keep that in the back of the mind. So all we are asking here is get me all the suffixes of ABC. So this produces ABC, BC, C, and empty list. So that's fine. And all I'm doing here is I'm swapping the order of suffix and prefix, right? So first I'm saying S is the suffix of ABC, right? And ABC is the prefix of ABCD. Again, this seems useless here. It is, but this is here for a reason. We'll see that in the next slide. If you ask this, you will see that it produces the same result again. But now let's do something different. So rather than using concrete lists, let's now actually use variables, right? So I'm saying, so the query says, X is the prefix of this list B, right? Singleton list with element B, right? And X is the suffix of the singleton list A. So what would be the result of X here? Yeah, okay. So let's try this, right? So we get false here, right? But if you try the other one, we actually get infinite execution. Actually, this I think will Stack Overflow. So X is the prefix of B, right? If you let me wait for, let me actually terminate this. I was hoping I can show you the Stack Overflow. I don't know how long this will take. Yeah, okay. So the Stack Overflow, right? It produces a very large result, but if you sort of focus on this, right? It says it's Stack Overflow. If you write it in the Prolog interpreter, then you will see that this one actually just produces Stack Overflow. So let's first ask this one, right? And so X happens to be an empty list, right? And then what we did is this produces false. So it's a really surprising result. What are the suffixes of so observe that for a suffix, right? So we only produce singleton list. Okay, so the way to read this is what is the list X such that A is the suffix, right? Sarthak and Aniswar, I think you sort of looked at the query in the reverse order. The way to read this query, right? This query alone is what are all the lists such that A is the suffix, right? So A is the suffix of singleton list A. A is also the suffix of some list with two elements where A is the last element. A is also the suffix of some list with three elements where A is the last element. I don't care about the previous two elements. And that is the reason why this one produced false, right? Correctly. Does that make sense, Sarthak and Aniswar? Okay, so you sort of have to be very careful in reading these clauses, right? So, yeah, so, okay, so this can be a bit backwards, right? We are always not calling a function. We're sort of declaring a query. So false is the expected answer, but this one Stack Overflow, right? And you can sort of imagine why that Stack Overflowed because of the reason why suffix produced lots of answers. The point here is that the Jupyter Prolog instantiation, right, always produces 10 results and stops, but Prolog itself keeps on going, right? So if I give, say, infinity here, this keeps on going along the search path. So the search doesn't ever terminate until you actually terminate the search. That is why this original thing is this one gives us false, but this one Stack Overflows. You should try it out, right? So I am not going to trace this by hand, but I recommend you to do this exercise by hand. I've done enough examples, so I want you to try to do this by hand and then convince yourself that this is going to Stack Overflow, right? So yeah, okay. So, but the observation here is if you switch the order in which we present the goals, it's going to Stack Overflow. This is what we expect, but the Stack Overflow, you should convince yourself why. Right? Yeah, again, you can see that this happens to produce interesting results, right? So again, I am so the reason why it produces interesting results is let's consider this one, right? Let's take this particular query, which is suffix followed by prefix, and I have the same query here, right, where I limit the results to 1. And so if you ask for the first result, it produces the correct one. So what are all the lists such that A is the suffix? So for that, there is one particular answer. The first answer is going to be the singleton list A, right? That is so A happens to be one of the results, and I am then asking what are all the L such that L is a prefix of ABC, right? And A happily satisfies that. So one intuition for where the infinite loop happens is here, right? Because I'm limiting this to one result that works out. The place where it goes into this infinite loop is when it fetches the second result, right? Because the Prolog Jupyter kernel tries to produce 10 results, right? It doesn't stop at 1. The first result is fine. If you ask for the second result, this is going to Stack Overflow eventually. So again, trace this by hand. The observation is that there are interesting behaviors. This produced false and stopped, right? The observation here is there are no results. And because we had prefix before suffix, it terminated. But if you switch the order, it goes into an infinite loop. So trace this by hand. You will, or trace this in the Prolog interpreter. You will see why this is the case. So yeah, I think this is what um, yeah. So I take this particular query, right? I ask for get me all the answers that you can produce for this query, right? So the difference between the query here and the query here is that I've swapped prefix and suffix, right? I swapped prefix and suffix. So that is what I have here. A suffix comes later, prefix comes earlier. I'm asking exactly one result here, and that is producing the only possible result, which is the singleton list A. But if I ask for the second result, this stack overflows. But if you swap the order, this produces exactly one result. I am not even asking for Prolog to stop at one, right? Prolog says I will explore the entire tree, but it happened to produce just one result. Trace wherever I've given trace this by hand, do trace this by hand, and convince yourself that you can arrive at you can convince yourself that the observation that you see here, the behavior that you see here, are consistent with what your understanding is, right? Okay, so that's the example for how the goal order changes the search, right? What we saw is if you have the goals in certain different orders, then it produces interesting behaviors, right? Because of the way in which Prolog picks the goals to explore. It is also the case that the rule order, the order in which you write down the program, the clauses, right? That also happens to affect the search for solutions. So what I have here is an append to function, right? Which is append function where the rules have been swapped. The order of the rules have been swapped. Append has this one first, followed by this clause. We've swapped it, and I've renamed uh, the predicate, right? So this is append to. So we have both append and append to now. So let's see what interesting behaviors this will bring in. So if you ask for um, 5 results, right? What I'm asking here is get me all the x and z such that if you append x to z, x to the singleton list c, I get z, right? And if I'm asking for 5 results, Prolog gives me 5 results. It says that if you take an empty list and append it to this list, singleton list c, you get z. If you take a list with one element, where the element happens to be _226, and you append it to the singleton list C, right? You get a list with 2 elements where _226 followed by C. And similarly, it produces more and more results, right? You can keep on asking more results. It will keep producing these results with variables, right? All of these are valid results, right? So this says any list with 4 elements appended to a singleton list C will give you a list with 5 elements where the first 4 elements are the elements from the first list and the last element is going to be C, right? This is what we expect. In append to, because we've reordered the clauses, even the first result goes down an infinite path. So this keeps on going, and this doesn't terminate, I think. Okay, this actually stack overflows as well. So this also stack overflows. Again, the reason is because of how we pick the goals. Trace this by hand, right? If you trace this by hand, you will figure out what is going on. You can also trace this by SWI Prolog. But tracing by hand is useful because you also think about unifications, right? So when you run it through just the Prolog interpreter, you don't explicitly see the unification steps and the unification failures. because Prolog interpreter sort of hides those behind. It doesn't show it explicitly. My recommendation is just go through what I've done. Um, right, so just write it down on paper and then sort of do the tracing. You will understand a lot about how unification works. Okay, I'll stop here. So any questions on this so far? So the takeaway um, from this part of this lecture is that you have to be really careful about the goal order and the rule order, because they change how the program works and what results you might expect. So you have to be cognizant of that as well, not just the logical description of the program. Okay, so I'll continue. So I think the first prologue lecture, I sort of mentioned this idea of Occurrence Check, but I said we'll come back to it later. So consider this particular query, right? So I say, get me all the E's such that if you take an empty list and append it to E, you should get the list which has A, B as a prefix and E as the tail, right? So if you think about this, this E is the same as this E, right? And you cannot have a list that satisfies this particular query. You cannot find such an E, because any E you can compute, that has to be the E that appears on the tail as well. So if you run through this, it goes down an infinite path. It doesn't terminate. I have to restart the kernel for this one. So let's actually look at what happens in detail. Oops. So let's look at what happens. So what are we doing here? We are considering append empty list E, and then this list where AB happens to be the prefix and E happens to be the suffix, right? So in order to unify this, what would Prolog do? Prolog will go ahead, and then this is append. So it picks the first clause, which is if you append empty list to any Y, then you get Y back, right? And so what will happen is empty list unifies with empty list, so that's fine. This Y will unify with this list here, right? So Y will be that list, and Y also unifies with E, right? We use the same variable there. So Y is equal to E, which is equal to A comma B with the tail E. In turn, what we say is we are unifying E with AB, where the tail is E, and we are going to try to find instances of these lists, right? The only solution for E here is E is A comma B comma A comma B comma A comma B, because you have A comma B here and then E. So you have to keep repeating A comma B infinitely. That's the only solution here. The problem here is that we are trying to unify two terms, right? I'm trying to unify E with some compound term, which also happens to have E in its body. So whatever solution I come up with E, I have to substitute that in the body of the term that I unify. So this keeps on going, right? I cannot find ground instances of this term ever. So Prolog will try to always find the ground instances. Ground instances mean there are no variables in that instance. So in order to compute the ground instance, it's going to say, okay, if E is A comma B with tail E, let me say, okay, this has to be A comma E, A comma B. The prefix has to be A comma E, B, and it keeps on going this way, right? So, and what you end up with is this infinite list with A comma B forever. And this is quite strange, right? So the reason for this is back in the days when Prolog was implemented, which is early 70s, right? Computation was really expensive, and it it sort of escapes me, but the designers thought that this occurs check is an expensive operation, checking whether when you are unifying two terms, whether a term appears in the body of another term. So you take two terms, L and R, whether L appears in or R appears in L was an expensive operation, right? And they said we won't do that check. That check is what is known as occurs check. Occurs check is the check where you are checking whether the left hand side term appears on the right hand side term, or the right hand side term appears on the left hand side term. Here the left hand side term is E. E appears inside the body of the right hand side term, right? So this is known as the occurs check. And in the name of efficiency, most Prolog implementations do not perform the occurs check. So they skip the occurs check. And that is what is causing the problem here, this infinite loop, because Prolog is trying to find the ground instance of this term, right? We have infinite loop on unification, right? So this is very bad. I think the efficiency of this optimization in 2020 is a little bit dubious. It's I think it's this just causes so weird behaviors that we should have the occurs check on all the time, right? Actually, some versions of Prolog do create cyclic terms. So we saw these cyclic data structures in when we studied streams in OCaml, right? Where we said, oh, you have a list with 0 and 1, and the tail of the list is going to be referred to the same term. Some Prolog implementation sort of resolve E as saying, okay, E is actually an AB, where the tail is going to be E. So they sort of live with that, but most Prolog implementations don't, right? So this occurs check is going to be an issue, and what SWI Prolog gives you is an explicit way of turning on and off occurs check. So usually occurs check is off, right? It is false. So you can explicitly set a Prolog flag for occurs check to true in the query prompt. So this is actually a query, but it is a special query that has some side effect. So you turn on the occurs check, and then you try to ask the same query, right? And if you ask the same query, then these two terms will not unify. So Prolog says that this particular thing does not have any solution. I mean, this is what we want, right? We don't want Prolog to go in an infinite loop here. So we also have another option for occurs check. It is not a Boolean value, but it takes 3 values. The third value that you can have is occurs check is an error. Whenever you find an occurrence, right? When you do unification, the left-hand side appears in the body, or the right-hand side appears in the left-hand side term. You actually throw an error. So this is what we get by occurs check is an error here. So let's make occurs check to be an error. That happens to be a query. So this is why Prolog comes back with true. But now if you do this, then observe that Prolog returns with an error where it said error occurs check something, right? So this atom appears in the body. I think the details are not important. I think this Jupyter Notebook is sort of not producing valid result, but I believe that SWI Prolog might produce something useful. Let's see if it does anything useful. So let me create a terminal, make it bigger. So let me turn on the occurrence check. I need the definition of append. So I'm going to take the definition of append. So user append control D. So that's loaded. And the query that I'm going to ask is this one. Yeah. So cannot unify some variable 9390 with this term, right? And this is just a substitution for this variable. So Prolog renames all variables. So all it's saying is at some point I'm going to unify these, and that fails, right? And you can trace this and see where the failure occurs, right? So there is a call to, you can see that there's a call to this particular clause which is going to try to unify, and that fails there, right? And it explicitly says would create an infinite tree. Okay. So this is Occurrence Check and Prolog. My recommendation is always have Occurrence Check to be an error, right? So it is never a good idea to have Occurrence Check. False is sort of I don't like this result, because whenever whenever you have this unification where Occurrence Check is there, like one of the terms occurs in the other term, it usually signifies an error, right? My recommendation is always to have this is an error, so that you can catch errors early and you're not surprised by um, the results that you see. So I'll stop here, and then we can continue in the next class. Any questions on this so far? No? Okay. So in which case, I'll stop here, and then you'll see the abstract interpreter for logic programs in the next class. And then at that point, I can release both the 6 and 7, and you can start doing those assignments. All right. So thank you very much. Bye-bye.